Welcome back. So we were talking about some training techniques and heuristics. Namely, we talked about initialization and normalization methods. Today, we're going to talk about another kind of method which is very essential for us, and that's automatic differentiation. So essentially, the idea is that we are training deep brain models using some variations of stochastic gradient descent that we're going to talk about in future lectures. But what all of them have in common is that we need to calculate derivatives. Okay, so calculation of derivatives or gradients is one of the crucial steps in all of the training algorithms that either we've seen, like gradient descent and SGD, or we will see very soon in future lectures. Okay, now it would be, because this is a repeating computation, it would be really good if we can automate this process. And in fact, modern deep learning frameworks or packages that we use to build, train deep learning models and use them for inference, such as PyTorch and TensorFlow, have done this automation. Okay, and what they do, they offer what we call automatic differentiation. Okay, so automatic differentiation, I would say, relies on two crucial ideas that we're going to very briefly talk about today. So these ideas are backpropagation method, okay, and computational graph. So backpropagation, as we'll see, is essentially identifying the structures from our model, as well as applying chain rules to very efficiently calculate the derivatives and partial derivatives of our, let's say, loss function with respect to the weights of each layer. Okay, so that's the main idea behind backpropagation. And computational graph is essentially going to help us when we apply backpropagation. So it's going to basically help us to see how different variables depend on each other. And we're going to use this graph in the backpropagation algorithm to calculate other variables. So essentially, and therefore apply chain rule. So let's talk about these two ideas. So first, we're going to talk about backpropagation. Now, we're going to do a very simple application of backpropagation, and we're going to just focus on one of the simplest models we can imagine, and that's a feed-forward multi-layer perceptron model. So let's consider our canonical training task, which is essentially minimizing some average loss. We want to find the best model that fits the data as well as possible. Okay. Let's consider a simple MLP, and let's assume that we have a regression task with a square loss. Basically, each sample loss is going to have a form like this. Okay, so where, as always, yi's are our labels. Here, I'm just assuming that my labels are vectors, like m-dimensional vectors, and this term here is basically the prediction of the model. So this is the MLP. Okay. And xi is basically the input features. Okay. Now, as you can see here, I have a multi-layer perceptron where I take the input, multiply by some weight vector, apply a nonlinearity, and then I feed this to the next layer, and I continue doing so until I feed everything to the last layer, apply the nonlinearity, let's say the ReLU, and then the weights of the output layer, and then I'll be done. So we basically have an MLP with m layers. And for simplicity, I'm assuming that the bias terms are 0. Okay, so we're not talking about that. All right, so what are our relevant parameters then? Those are basically the weights of each layer. Okay, so W1 through WL. And these are typically matrices, and in fact, in practice, are tensors, right? But from, let's say, a mathematical perspective, it is easier for us to think of these as, let's say, a very big vector W, which is in RD. Okay. All right. So what is our algorithm? Let's assume that we are using SGD, or stochastic gradient descent. We have this very simple update. Okay. So next parameter is the current one minus some layering rate times the stochastic gradient GT, and GT, as we have talked about before, basically is representing the gradient of the mini-batch of samples that we are, let's say, selecting and processing at time or iteration t. Okay, so to update the parameter, therefore, what we will be doing, we'll be updating each of these weight matrices W1 through WL. Okay. So therefore, to do that, we need to find the partial derivative of the loss with respect to each of these weight matrices. Okay. And we're going to do that by applying chain rule. Okay. So the idea is that if I ignore the structure of my model and therefore my loss function and perform the calculation naively, it's going to be computationally prohibitive. But if I identify the structure, as we will talk about, and leverage that, I can accelerate the computation and do that a lot more efficiently. Okay. Now, for our discussion in the rest of the lecture today, I'm going to basically treat this W as a big vector. Okay. So it's a matrix. Let's say we flatten it out or like vectorize it such that it's a DL times DL minus 1 vector. Okay. So DL is basically the number of outputs of layer L, and DL minus 1 is basically the number of inputs to that layer. Okay. Now, given that this is basically a vector and my loss is a scalar valued loss, the partial derivative is also going to be a vector. What's its dimension? The dimension is exactly DL times DL minus 1. Okay. So the reason I'm talking about this here is that I would say potentially the most confusing part about the chain rule when you talk about it in the context of vector valued or matrix valued vectors and matrices is to keep track of the dimensions, right? And we basically have to employ certain operations to make sure that everything matches, the dimension matches, and our expressions are correct. So these are things that we don't necessarily have to deal with when we are talking about scalars and basically derivatives in one dimension. All right. So as I said, the main idea is to identify and leverage structures. To do that, we're going to define certain variables, and we'll see how each of them will show up in basically the expression for the partial derivative of the loss with respect to our parameters, which again are basically the weights of each layer. Let's define two vectors first. I'm going to define the pre-activation vector, and I'm going to call that V, and also post-activation, I'm going to call that H. Okay. So mathematically, this is what I'm doing. So pre-activation is basically the weights times the output of the previous layer, which is basically the input to layer L that I'm considering here. And then I take this pre-activation vector and I apply my activation function, let's say ReLU, such that I can get the post-activation vector. Okay. And note that these pre-activation and post-activation vectors have the same dimension, and their dimension is d sub L. Okay. And we define this for each layer from layer 1 up to layer capital L. And based on this definition, it's not difficult to see that H0 is basically our input, and V sub capital L is basically the output, the prediction of my model, basically Y. Okay. All right. So these are the first two variables that we'll define. Let's also define what I call the final error signal, and this is basically the partial derivative of the loss with respect to the pre-activation of the last layer. So basically with respect to the output, the prediction of our model. Okay. So this is not necessarily something that we'll see immediately impacting the partial derivatives, therefore the update of each weight matrix. But as we'll see, and we actually did talk about it very briefly in some of the previous lectures, this is something that will actually show up in the partial derivatives. So that's the main reason we are defining that. So, and the reason we call this the error signal is that this is going to be basically the difference between our final prediction VL and the true labels. So if I'm not making any errors, this error signal will be 0. Therefore, the gradient is 0, and we are not updating our parameters. On the other hand, if I'm making some errors during training, this error signal is large, which means that the gradient is non-zero and large, so I'm going to make more progress. I'm going to update more my parameters a little bit more compared to the case where the error is smaller. All right, so this is the third variable, and finally let's also define the activation derivative matrix. Okay, so obviously when we are talking about the partial derivatives, if I change the activation function, I'm also changing those partial derivatives. So that's why it's essential to also define this matrix. So this is basically a diagonal matrix that has on its diagonal the partial derivative, basically the derivative of the activation functions. Okay, so sigma prime is basically the derivative of, let's say, sigmoid, if my activation is the sigmoid, or the derivative of ReLU if my activation is ReLU, and so on and so forth. Okay, and given that we are applying activations to vectors coordinate-wise, so the input to the activation is basically a vector. That's why I have to stack the vector of all of these derivatives as diagonal of a matrix. Okay, and once again, why do we need the matrix? Because we are working with vector-valued quantities, so we have to do certain operations such as diagonalization to make sure that everything will match in terms of dimension and our expressions are correct. All right. So now, given that we defined this, let's actually go and see what's the form of these partial derivatives. Okay, and let's start with the partial derivative with respect to WL, capital L, which is the base of the last layer. Okay, now let's apply chain rule. Okay, so chain rule basically says that the derivative with respect to WL is basically the derivative of the prediction, final prediction, or the last pre-activation with respect to WL times the gradient of loss with respect to VL. Okay, so this is nothing but chain rule, and it should be intuitive. It's just that again, because we are working with vectors and matrices, we have to make sure that the orders are in the correct order, such that everything again matches, the dimension matches, and our expressions are correct. Okay. In this case, this is something we actually calculated before, and we actually named it the final error signal. So this is going to be just the difference of our prediction and the true labels. So this is exactly EL, and it's a vector. Its dimension is DL times 1. Okay. Now, this first term might be a little bit more confusing and complex, but let's actually recall the definition of VL. Let me write it here. VL was basically WL times HL minus 1. Okay, so intuitively, this is something that is linear in WL. So when I take the derivative with respect to WL, the result is basically independent of WL and only depends on HL minus 1. And this is indeed true if we were talking about scalars. For instance, let's say I have some function f of x, which is 5x. Okay, when I take the derivative with respect to x, f prime is 5. So this is exactly what we are dealing with here, except that what we are taking the derivative with respect to is this huge vector. So we have to again introduce some operations to make sure that the dimensions match. In this case, we have to introduce what we call the Kronecker product, okay, between an identity matrix with appropriate dimension and HL. But all that matters is that the dimension of this matrix is such that the final partial derivative has the correct dimension. And the dimension is basically, again, a vector of size DL times DL minus 1. Okay. So here I have a simple example to show what Kronecker product means. Okay. So let's say that I have, again, a vector-valued function. I'm taking the derivative with respect to this matrix W. So it's not going to be too difficult to show that the derivative is actually going to be this matrix, which is 6 by 3. Okay, and canonical product basically takes this vector A and repeats it in each column by shifting it appropriately. Okay, but long story short, the first term only depends on the post activation of the last layer. Okay, so that's what matters for us. All right. So here basically, therefore, we see a structure that the partial derivative depends on the error signal as well as the post activation of the previous layer. Okay. Now let's see whether we can identify a similar structure, not just for the partial derivative with respect to weights of the last layer, but for all layers. So that's what we want to do. Recall our definition of the pre-activation and post-activation, this and this. Okay. Now let's do a calculation we did in the previous slide for layer L minus 1. Okay. So the partial derivative is the derivative of the partial derivative of the post-activation of L minus first layer with respect to WL minus 1 times another partial derivative, okay, and times another partial derivative, and finally the partial derivative of the loss with respect to the predictions. Okay, so this is basically the final error signal. This is again, it's not easy. It's not very difficult to see that it will be something that depends on WL. This guy, the partial derivative of HL minus 1 with respect to the pre-activation of layer L minus 1, layer L is basically something that will only depend on the activation derivative matrix. And finally, this guy is going to be something that only depends on HL minus 1. Okay, so I am hiding certain operations such as canonical product with an identity matrix. We may need a transpose or things like that. But all that matters is that, again, these terms only depend on what I'm writing underneath each one. Okay, but we have to, again, introduce certain operations to make sure that our final answer is a DL minus 1 times DL minus 2 vector. Okay. So what is this term? Again, by chain rule, it's not difficult to see that this is going to be the partial derivative of loss with respect to the output of the L minus first layer. Now, this is the part that we now identify a structure. So what's the structure? So let's go back. The partial derivative of loss with respect to the weights of layer L is basically the partial derivative of the output of layer L with respect to WL times the partial derivative of loss with respect to WL. For layer L minus 1, again, the partial derivative is the partial derivative of the output of that layer with respect to its weights times the partial derivative of the loss with respect to output of that layer. Okay, so this is exactly the same as what we had for layer L. Okay, so therefore it is meaningful to also give this guy a name, which we will basically call it the error signal for layer L minus 1, as opposed to the final error signal that we defined earlier. Okay, so what's its definition? Basically, this is something that is the product of the activation derivative matrix of layer L minus 1, the weights of layer L, okay, and the final error signal. So this is as we can see here, I'm talking about, let's say, layer L minus 1, and in particular a quantity that is important to calculate the partial derivative of loss with respect to weights of that layer. But this quantity depends in some sense on future values. Notably, it depends on the weights of the next layer, as well as the error signal for the next layer. So therefore, this basically gives us a procedure on how to calculate the error signal for layer L-1. If in some sense I would be able to traverse the network backward, I would be able to propagate these values, then I'll be able to calculate this error signal, and then I'll be able to calculate the partial derivative loss with respect to the weights of this specific layer. And this is exactly the backpropagation method that we're going to formalize in a few minutes. Okay. So therefore, this is what we observe, that for layer L-1, the partial derivative is basically the partial derivative of VL-1 with respect to WL-1, and this is nothing but the post-activation, the post-activation of the previous layer times the error signal of this layer. Okay. So as I mentioned, therefore, this gives us a natural procedure to in some sense leverage memory, meaning we calculate certain quantities and store them in memory for the sake of reducing the computational cost of calculating gradient. Okay? And this procedure is called backpropagation. What do? So we notice that we have to calculate certain quantities, notably the pre and post activation vectors, in order to calculate partial derivatives. So what we'll do is that we're going to calculate them in what we call the forward pass. Okay? So we traverse the network from the input to the output, forward pass, and store the pre and post activation vectors in memory. And then in the backward pass, I'm going to propagate the errors. So I first calculate the error for the last layer. I propagate that back to calculate the error for the layer L-1. And by doing so, I'll be able to calculate the partial derivatives of the loss with respect to weights of that layer. Okay? So in particular, this is basically how the error signals for one layer depends on the error signal for the next layer. Okay? All right. So that's the first main idea behind automatic differentiation. Okay. So backpropagation that requires traversing the network in two directions to calculate certain quantities, storing them in memory, and then eventually calculate the partial derivative. Now, in practice, the computation is actually sort of guided by what we call computation graph. So computation graph is basically a directed acyclic graph that represents the sequence of operations applied to variables. So operations, in this case, these products, right? And our variables are basically the pre-activation, post-activation, etc. So this is an idea that I would say transcends the concept of deep learning that we are talking about here, and it is pertinent certainly in various computational frameworks. But we're going to talk about this a little bit in terms of calculating the derivative, right? So which is basically what we need when we want to update weights of a deep learning model. Okay. Now, computation graph basically helps us to track how each value depends on others. In particular, for instance, how let's say one pre-activation depends on the other pre-activations, how one error signals depends on another error signals, etc. Okay. And in the context of deep learning, and notably automatic differentiation, what we'll do is that we're going to traverse this graph, okay? So in forward direction to calculate these quantities, and in the backward direction to apply chain rule and therefore apply the backpropagation method, okay? So to see this idea, I'm going to go over a very simple example. So our example is that I have a function f of x, which is basically 2x plus 1 times 2x plus 1, okay? And my goal is to calculate the derivative of f at x equal to 1. So obviously this is very simple to do, right? So f of x is nothing but 2x plus 1 squared. So therefore, its derivative is basically 2 times 2 times 2x plus 1, such that f prime at 1 is basically 2 times 2 times 2 plus 1, which is 12. Okay. So we're going to see how we can reach the same answer using computation graph and basically chain rule. Okay. In this case, basically the backpropagation algorithm. So to do that, we're going to think of we're going to make things complicated. Okay. So we're going to think of this function as some other function h, which depends now on 2 variables, x and g. Okay. What's the dependence? Basically, the function is g times 2x plus 1. Okay. Now, what's this other variable g? It's just a function of x, and it basically takes x and returns 2x plus 1. Okay. It's not difficult to see that this is exactly our original function. Okay. So if I calculate, therefore, the partial derivative of h with respect to x, I should be able to calculate the partial derivative of f with respect to x as well. All right. So therefore, we're going to define a graph, and this is a graph where we have certain nodes. Each node is a variable, and basically the edges help us to see how the variables depend on each other. Okay, so we have 3 variables here: x, g, and h. Okay, and here is the dependency. So g was basically 2x plus 1. So therefore, there should be like a directed edge going from x to g. H depends on both g and x, so there should be one edge going from g to h and another directed edge going from x to h. Okay, so this is basically our graph. Okay, so we define the graph before doing any calculation. Okay. Now in the forward pass, this is where the calculation starts to happen, right? So we're going to calculate these certain quantities. Namely, we again, in the context of deep learning, we're going to calculate pre and post activation vectors, okay, such that we are ready for the backward pass, where we propagate the error and therefore calculate the partial derivatives. Okay. In addition to calculating these input variables, we're also going to label the edges with relevant partial derivatives. Okay, so let's do this calculation then. First, we'll see what are each of these input variables. So x was equal to 1, that I know. Given the dependency of g on x, g will be 3. And finally, given the dependency of h on both x and g, h will be 9. Okay, so this should be easy to see. Now, on the edges, we're going to basically write down the partial derivative of each variable with respect to its input variable. Okay, so here my variable is g. The partial derivative with respect to its input x is going to be 2. H has 2 inputs. One is g, another one is x. Okay, so on this edge, therefore, I have the partial derivative of h with respect to g, which is nothing but 2x plus 1. When I plug in x equal to 1, the answer will be 3. And then finally, the partial derivative of h with respect to its other input x here is going to be 2 times g. Okay, again, when I plug in the value for g, the answer will be 6. Okay, so therefore, we have successfully completed the forward pass. We went from this side to the output. Along the way, we calculated the important variables and also named these edges with relevant partial derivatives. Now we are ready for the backward pass. So in the backward pass, we are basically propagating the error signals we talked about before to calculate the partial derivative of the output with respect to the input. Okay. So here's how we do. And in this process, we are going to basically apply chain rule. And that requires us to accumulate the derivatives and sum them over all paths. Okay, so let's see what I mean by that. So first of all, here, I'm going to write the partial derivative of my function with respect to h. So f was exactly h, so the partial derivative is equal to 1. Okay. Now, here I'm going to write the partial derivative of my function f with respect to this variable that I defined, g. By chain rule, this is nothing but the partial derivative of h with respect to g, and then f with respect to h. Fortunately, I have both of these quantities calculated. So this is always equal to 1. So this guy. And this guy I already calculated in the forward pass. So therefore, I'll be able to calculate the partial derivative of f with respect to g. Okay. So this is equal to 3. Now, so in this example, there are two paths from output to the input signal x. Okay. So as I'm going to talk about here, we have to accumulate these partial derivatives and then sum them up across all paths. Okay. So this is basically the partial derivative for this variable. Now I'm going to calculate the partial derivative of f with respect to x, so which I'm writing here. By chain rule, this will be the partial derivative of h with respect to x, which is something I calculate in the forward pass, times the partial derivative of f with respect to h, which I've calculated here. So this is basically the accumulation of derivatives for this path, but there is another path from output to input, and that's this path. So I have to also accumulate the derivatives and then sum the result of with the calculation I've talked about here. So therefore, there is another term. What's the other term? Is basically the derivative of h with respect to derivative of f with respect to h, which is 1. So now I'm moving along this path, plus the derivative of h with respect to g, which is 3, something I calculate in the forward pass. And then finally, the result is nothing but the product with the partial derivative of g with respect to x, which is equal to 2. Again, something I calculate in the forward pass. So therefore, when I do this accumulation, I'm going to find that the partial derivative is nothing but 12, the result that we expected to see. Okay. All right. So this example is basically an example of a static computation graph, because we defined the entire graph before execution. Okay, so the graph is defined before we start the process of backpropagation and calculating, let's say, the pre and post activations and in the forward pass, and also propagating the error in the backward pass. Okay, and this is indeed an approach that we took when we defined the earlier versions of one of the most famous deep learning packages, which is called TensorFlow. Okay, and in some sense, this is intuitive to be called the define then run approach, because we are defining the graph first, and then we are running the calculation. Okay, and there are advantages and disadvantages here. So the most important advantage is that it is highly optimized. Okay, because we know the computation graph in advance, and are later on, when we basically run or execute, the computations will be highly efficient. Okay, but the disadvantage is that this is not very flexible, and also more importantly, the debugging process is going to be difficult. Okay, because if there was some bug happening when we define the graph, we're not going to see that bug or face that bug or even notice the bug when we define the graph. We're only going to notice it in the execution phase of our computation. So this therefore leads to what we call dynamic computation graph, to try to make sure we have more flexibility, and also the debugging process is a little bit more easier. Okay, so in the dynamic computation graph, we are basically building the graph on the fly during the execution phase. Okay, so this basically means that the structure of the graph can change at each iteration. So our approach is basically defined by run approach. Okay, and this is the way we construct the computation graphs and basically perform backpropagation in modern deep learning packages such as TensorFlow 2.0 and PyTorch. Okay, so the advantage is that it is flexible, given that the graph is defined in a dynamic way, and it's also easier to debug, and in some sense, it's also more intuitive for development, as when we talk about more complicated models such as recurrent neural networks, or when we use deep learnings in contexts beyond supervised learning, such as reinforcement learning. The disadvantage is that we're gonna basically now lose some optimization. Okay, so because we don't know the graph before computation starts. Okay, so therefore it could be slightly slower compared to the static graphs due to this runtime overhead. All right, so this is basically a short lecture on two important ideas that we need when we want to calculate the gradients efficiently in the context of deep learning to make sure we can have efficient training algorithms. In the next video, I'm going to talk about a very brief example of how we basically deal with these ideas in practice when we use deep learning packages such as PyTorch. I'll see you soon.